Alright, here's another challenge problem for class. This is the third one I have. So what she gave us is this ODE, and it has this phase line right here. So 2, 0, -2 are the equilibrium points. And then we got to find a step size. So in Euler approximation with initial condition y0 equals 1 zigzags around the correct behavior. So what I did here first was just to prove that these were the equilibrium points, which I found were. And then y of 0 is also just this, which is initial condition. And then I plugged it into the derivative, which is this, and I got -3. So since the derivative is negative, the yt solution will decrease from 1, and it will approach the stable equilibrium at y equals 0. So without ever crossing it. So that just proves that. And then the Euler's method right here I put down. And I put h as the step size, and then fy equals this. Oh, I also forgot that I changed this to this right here. That's another thing I did. Sorry about that. And then, yeah, so I just put that to equal that. And then for the first step, it's just y1. So then I filled out this right here. And then filled in 1, everything. 1 minus 3h is the first one. And then so I found the step size for this. So I made the equilibrium point equal 0 for a zigzag. And this is what I got. This, plugged in that, h is greater than 1/3. And then preventing divergence, I put y equals -2 as an equilibrium point for this one. Because while it needs to overshoot 0, it must not overshoot the next equilibrium point. So it can't go over 0, so I put -2 instead. So it can't be +2. And then this equals h is less than 1 for the step size. And this whole thing right here zigzags. So if h equals 0.5, which is in the boundaries, then y equals 1, y equals 0.5, so it goes up, boom. And then y2 equals 0.43, boom. Okay. And then the next part I did was I solved this question. What about y2 plus or minus infinity, or something that overshoots then corrects? So yeah, this one's kind of a difficult problem, but so what I did here is, let's see, y is less than -2, yep. So if the approximation dropped below -2, the derivative becomes increasingly negative. Because the slope is negative and very steep, Euler steps will rapidly accelerate downward to -infinity right here. So that's why I kept it as -2. So I'm making it go down from -2, from the equilibrium point from before. And so that gives me h is greater than 1. So that solves the first part. And then the or something that overshoots then corrects is right here. So what I did is f derivative y equals 3y squared minus 4. So this overshoots when h is greater than 1/3, and then corrects when y equals 0. So what I did again is just put a Euler's method, and I figured this out. And then I put that right here, and I made it less than 1 and greater than -1 and less than 1. And then so I solved it out, and then when you divide, it switches signs. So then I got this. And then to satisfy both conditions of when it overshoots and corrects itself, it actually has to be this. So I could have drew a graph. I mean, if someone wants a video about this and wants to draw the graph about it, I mean, like, once it goes, like, it super zigzags at, like, 0.86, but then, like, it's off-center. Like, it doesn't correct itself. And then when it goes past 1, there's no zigzag at all. And then when step size is 0.1, there's, like, no zigzag at all. So that's the thing that has to satisfy both conditions.